Hello everyone. Today we'll be doing a complete editorial for Codeforces Round 834 Div 3. I would highly recommend you to pause the video at any point in time if you haven't tried any of these problems, and feel free to discuss any of the different approaches in the comment section down below. So without wasting any time, let's get started. Let's start by understanding the problem statement first. So we are talking to Polycarp, and if he has to say a yes, then he'll say yes many times in a row. So for example, if he wants to say yes, he will say yes like this concatenated several times. So let's just say that this substring is our yes concatenated string. Because of some noise, we only hear a part of that answer. That means a substring of it. And that supposed to be substring is given to us is the input. And we have to determine if this given input string is actually a substring of our yes concatenated string. Let's try to understand the question with the help of an example. So, for example, we can hear this part as ESYES, or maybe we will be hearing just Y, or maybe we will hear an SYE. So, these are several possible substrings that are possible. So, let's try to come up with an approach now. So the first thing that comes to our mind is that if the input string, let's suppose input string, contains a character that doesn't belong to YES, then the definite, basically we have a character that is not inside the YES, then definitely the answer will be no. Also, a point to be noted here is that YES given to us is case sensitive. So even if the input has a yes in the answer, but let's suppose all in caps, then also the answer will be no. So how do we solve this problem now? So let's start by comparing the first character itself. So for example, let's take the first input of the sample test cases ES by ES, and also declare a string yes, that is our key string over here, and call it Y. So let's start off by finding the first character in the given string itself. So we can find that it happens to be at position number 2, position number 1. So this is the position where our first character is found. I'm using zero-based indexing. That's uh, just more suitable for me. And let's see what can we do after that. After this, the question is actually pretty simple. We can simply compare this by using a loop in the cycle. So how do we run a loop in the cycle? That's another main question for the implementation. So let's see if I have I equal to, let's suppose I'm using the variable I to iterate in yes string, my y string, cyclically. What can I do? Let's see how this will run. 0, 1, 2, then I wanted to come back to 0, then 1, 2, then I wanted to come back to 0, and so on. Okay, so how do we do this? It turns out that it's pretty easy to do this. We can just simply mod it by the length of the string, and the length over here happens to be 3. So for example, I'll just increment I and I'll take a mod with 3. So let's see, it will be 1. So let's suppose I'm starting with 0, it will be 0, then it will go to 1, it's gonna be 2, now 3. But we take a modulus of 3 with the length that is 3, it will give us 0. That means resetting the value back to the first character. Similarly, we can do this, and another again it will reach 3, we'll mod it with 3, and we'll get a 0 again. So this way we can run the loop in cycles. So let's see what we have already done. We found the first character in the string, found first character. We also know how to run a loop in cycle. So let's call this a cycle loop. So we know how to do these two things. Now let's try to solve our problem again. If at any point in time we, let's suppose, do not find our first character, the first character is not present. Basically, it's not present in our y string. Then the answer will be no, definitely. Also, if at any point in time, if there happens to be a mismatch, so for example, if this was a small y, then what will happen? So E and S will compare fine. We'll reset our I back to capital Y. Now capital Y and small y will not match. So at that point in time also the answer will be a no. If we have a successful comparison, only in that case we'll print a yes. So let's hop on to the actual accepted code. So here's the code. So I created a solve function that will be called the test case number of times. And so let's see the answer for a particular test case, how to solve it. So I also have two strings declared yes and no, so that I do not have any, so that I can just print them more conveniently. I'll be using C++ as the explanation language. You can use either of your choice. Just understand the logic and it will be really easy to implement. So I take in the input as the string s. I declare my y string as yes. Now I'll try to find the position of that first character. So for example, in the in this case, I'll try to find the position of e first. That's what we did as our first one. So let's see that. So I'll declare I equal to 0 until 3. So I'll be a yes. And if I find a match, then I'll just simply break out of the loop, else I'll just move on. So if I equal to 3, that means I did not find my character and I didn't break out of the loop. I'll simply print a no and I'll return. Um, so let's suppose that we now it's a guarantee that we found our first character at certain position. Now from that start position, we can simply just iterate in cycles as I explained earlier. So for character C in S, so if it is not equal to y at I, basically we are comparing the characters, and there is a mismatch, we simply print a no. Otherwise, we'll just continue in cycles till the time we completely iterate our input string. Now, if there is a complete match, in that case, we'll print a yes, and the function will return automatically. Let's discuss the problem B now, the lost permutation. A sequence of n numbers is called a permutation if it contains all integers from 1 to n exactly once. The sequence can be totally random over here. So for example, the sequence 3142 contains all the elements from 1 to 4 exactly once. So it is a permutation. 1 is a permutation to 1, likewise a permutation, and the next examples are not. Polycarp lost his favorite permutation and found only some of its elements, the numbers b1 to bm. Therefore, we can say that Polycarp believes that the m numbers he found are a part of his favorite permutation that he lost. He is sure that the sum of lost elements is equal to s. So the sum of remaining elements that he was not able to find have a sum equal to s. Determine whether one or more numbers can be appended to the given sequence b1 to bm. So the m numbers that he found, such that the sum of added numbers is equal to s. That means that we have to add certain numbers that have the sum equal to s, such that the entire sequence becomes a permutation of any random n. Um, and the resulting new array is a permutation, as I said. So we have to tell if it is possible or not. So let's try to build an answer using the given data. First thing that is given to us is that Polycarp already has B1 to Bm numbers. Let's call this sequence B. And so in order to have a permutation that satisfies these constraints, we can immediately observe at least two things. So one of those is that B1 to Bm should all be unique. So these should all be unique. Only then can it form a permutation of any random n. And secondly, in order for this to be a permutation, we should have all numbers from 1 to max of bm. Alright, so these are the two very basic observations that we can make immediately and intuitively as well. Let's see what else is given to us. So we are given that the sum of rest of the elements is s. So this is the sum of lost elements. Okay, so how can we use the sum? Now we know that we are building a permutation, and the observation that comes in from this part is that we know that sum of n natural numbers is equal to n into n plus 1 by 2. So how can we use this thing? So we can say at any point in time, we definitely have the sum of a permutation of b, which means if I call the maximum of b as let's suppose a, then we definitely have a into a plus 1 by 2 as the sum. Now, how can I get this? If I add s with b, with the sequence of b. So basically, if I say that I add s with the sequence some b, then it will definitely be sigma n for any random n. So n can be anything over here. So I have a current sum and I have to be sure. So let's say that this is s. Okay. and I have a current sum which will correspond to this thing, this expression right over here. Now, if I have to keep B as a permutation beyond this thing, I have to be sure, exactly sure, that I keep on adding the element which is max of B, which I said is A. So we can say A. What do you think should be the next element that I add to B so that it still remains a permutation? You are exactly right. It should be A plus 1. Then it should be A plus 2, and so on. Now, we also have to decide a limit for this thing. So, if the sum of this entire thing at any point is equal to S, this means that congratulations, we have achieved the goal, and the answer is yes. But if at any point in time this expression exceeds S, that means that there was no natural number n such that all the conditions were true. In that case, unfortunately, we cannot build such a permutation. So let's hop onto the code and see how we can implement this thing in a very easy way. So here is the accepted code. So I take n and s. So n is the number of elements and s is the sum of those lost elements. Int a. So I took the permutation of m elements, that was b1, b2 till bm, as a. Okay. I take in the input. Now I calculate the maximum element and also the current sum. So this is nothing but n into n plus 1 by 2. I just like using bitwise operators more. So this is the current sum that we have, and S is so I add S to the sum of the provided elements. Now it was guaranteed that B elements are already unique, so it says that they are all distinct integers and also they are from 1 to 50, which means that we do not need to worry anything about them being unique or satisfying the permutation constraints. Now I added S with the remaining elements so that I am sure that S has to be like, so that now I can check if current sum is equal to part of the sum of a natural number sequence. Now I'll just simply say that while CS, that means current sum, is actually less than the required sum, I'll just increment the max and do an A plus 1 kind of thing over here. So this is exactly same as doing this part over here. Okay. And the moment CS is greater or equal to S, we'll break through the loop. If it is equal to the required sum, then we print yes, otherwise we print no. So that's it for problem B. So the next problem is C named thermostat, and the problem was fairly simple, though it took me a few attempts to solve this problem, but we can ignore that fact. So the problem states that Vlad came home and found that someone had reconfigured the old thermostat to a temperature of A. The thermostat can be set to a temperature from L to R inclusive. The temperature cannot be changed by less than X. So basically, the thermostat can only be altered in a range from left to right, or that range is inclusive. And whenever you change the temperature, it has to be changed by the least amount of X. Then the formal mathematical configurations are given for that. And let's see further. So you are given L, R, X, A, and B. Now what are these? L is the left range, R is the right range, X that minimum amount that we need to change at once, A is the new temperature that someone had set, and B is the temperature that we are willing to set from A to B. So we have to find the minimum number of operations that are required to change the temperature from A to B, or claim that okay, it's impossible and we simply cannot do that. So let's hop on right to the code part, and this is how I solved the problem. So this is nothing but a case ladder kind of stuff. So when can we say that we'll require exactly zero operations? Well, okay, that's obvious. When A is already equal to B, we do not need any operations, and we can simply print that we will require zero number of operations. Okay, when will we require one number of operation? Well, this is also fairly simple to figure out. Whenever there is a distance between A and B is greater than or equal to X, then definitely we can do hop between the two in just one operation. Okay, when is it that we'll be requiring two operations? Well, this can be a bit tricky, but let's see how we can do that. So let's suppose I have left range over here, right range over here, um, A over here, and B over here. And let's suppose that X is little big. So in this case, I would like to jump from A to any extremity. It might be L, it might be R. So let's suppose for the take an example, I jump to right and then I jump from right back to B. Of course, I would like to jump to the extremity so that while coming back, I can make sure that the difference, that means the extent by which I'm changing the temperature is farthest from B and I'm able to make valid moves. So this can be also done for the left extremity. So let's see how we did this in code. So if I can hop from L to B in a single step, and also I can hop from A to L or L to A in a single step. Similarly for the right extremity, in that case I'll just require two moves. Okay. Besides that, there's a tricky case. If I can make any, so basically I had already covered all the cases. So this part I coded with the help of the exclusion type of stuff. So basically, if I can make any valid move from A to X, so from A to anywhere, and any valid move from B to anywhere. So I claim that I'll require three moves. One such case that I was able to come up with is like this. So for example, if A and B are fairly close, similarly L and R are fairly basically this is kind of case. But so for example, I can go from A to R, but I cannot come from B R to B back. So in that case, I will have to go from R to L, then I'll be able to come to B. So this is one such case that I was able to come up with for the three operations required. And if that is not the case, then definitely we cannot change. So there is no valid move, and I'll have to print a -1. And that's exactly what I did over here. If there is any valid move from A to any extremity and from B to any extremity, in that case the answer will be 3. Otherwise, I just say that it is just impossible to do so. Next up is problem D, make it round. So inflation has occurred in certain place, so the store needs to change the prices of goods. Okay, the current price of good N is given. Okay, so the price of a certain good is given to us, and that is equal to N. It is allowed to increase the price of good by k times, and k must be from 1 to m, anywhere, both inclusive. So basically, we can multiply the current price with any number between 1 to m, both inclusive. So the output, the roundest possible new price of the good. So by roundest possible, we mean that it should have the maximum number of zeros towards its end. So for example, 10 is more round than 100. So, and if also it says that if there are several possible variants, output the one in which new price is maximal. So, for example, if we can make price 100 and 200, then we have to print 200 instead of 100, even though both number have equal amount of roundness in them. Okay. So, if it is impossible to get a rounder price, then output n into m. So basically, just multiply the current price with the maximum. Just make it maximum possible using the m as the multiplier, and just print that if we are able to, if we are unable to get anything round out of it. So this problem was very observational based and requires very less knowledge of maths or anything. But yeah, so let's just see how we can solve this problem directly. There's not much of the things that we can infer from the question directly. So let's take an example. So we are given 6 and 11 as the first sample case. So this is m, which means that our k can be anything from 1 to 11, and this is the current price. So let's see what all we can get. So I'll just try to write k from 1 to 11 and multiply it. So it will be 6, 12, 18, 24, 30, 36, 42, 48, 54, 60, and 66. In over here, we can see that we have we got two round numbers of equal roundness, that is 30 and 60, and in this case, of course, 60 is the greater one, so this will be our answer. Now, how can we achieve this answer? Of course, we cannot loop entire k to m, and the constraints will obviously give us a time limit exceeded because m, I think, goes till 10 raised to 9. Yep. So what can we do here intuitively? Now, one thing that we can observe is that in order to get a 0, that means that we have something 10 to the power something as our multiple. So this has to be a factor of that. Okay, then how can we break 10? So 10 is nothing but number of 2's and number of 5's in the multiple. So minimum of these will actually be equal to the count of zeros that we get. Okay, so this is one thing that which is really obvious. So for example, if you say that how many times 6 will be a factor, then it will be the minimum of number of 2's and 3's in the factor. So this is a very normal thing to observe. Okay, but how can we use this thing to solve our problem? So let's hop on into the code and see how we can use this thing very easily. So here's the accepted code, and I again have a solve function that will be called the test case number of times. So one thing to be noticed over here is that constraints are really big, and we must use long as the type, and teacher will obviously result in an overflow. So I take an input the n and k. So instead of m, I took the input as k. Um, I define a function. This is a lambda function. You can define it normally as well if you are not very comfortable with this kind of syntax. But for now, let's just say that this is a function. It takes two parameters, x and y, and let's see what it does. It says it's equal to 0, and while not x and y, x modulus y. So this means that x has to be divisible by y. Only in that case the loop will work. Okay. So we say our C++, so C is our counter and X is divided by Y. So basically it is giving us the maximum power of a number that divides X. So for example, X is 16 and Y is 2, then the answer will be 4. So that's what it means. Okay. So the count of twos that divide, or basically you can say that the power of 2, the maximum power of 2 that divides n is 2, and same goes for 5. Okay, now I also created a check function. uh, so let's see what does a check function do. So it captures everything by reference. So I'm using already declared variables in this function without passing them as parameters. I taken a number z as the parameter. Then I define something like RT and RF. So this is the required number of twos and this is the required number of fives. What? Okay, so this is actually the required number of twos and fives in order to have the maximum roundness. So Z means that the number of zeros. So how many zeros can I get maximum to the right of the new price? So that is what it means. Okay, so the required number of twos will be z minus 2 or max of 0. So basically, I already have a certain number of twos, and if I want to get 5 zeros towards the end, then I must at least have 2 to the power 5 as a factor of the current number. Okay, same goes for 5. If I need 5 zeros towards the end, then at least 5 fives should be there. So 5 to the power 5 should be a factor of the number. Then I take a number. I say while RT minus minus. So while required number of twos I decrease and I multiply the number with 2. So this is the required power of 2 that is, so this is the power of 2 that is required even further than what I already have. Same goes for 5. So I'll get a number that is the least requirement, that is the least possible requirement to get these number of zeros. So this is a little tricky part. Just bear with me and try to understand it as better as possible. Then, let's try to write this thing down once again. Okay, so let's take this example only, 6 and 11. So if I want to get, let's suppose, uh, one number of 0 towards the end. Okay, just one zero. I don't care what it will result in, 60, 30, 20. I don't care about that. I just say that, okay, I just need one number of zeros. So how many number of twos are already there in 6? So 6 can be actually written as 2 into 3. Okay, so there is already one number of 2 present over here. So that means that I do not require any further 2's in order to get a 0. So okay, so z over here will be 1, and 2 I already have is 1. So the required number of 2's will be 0. No, number of 5 I have is 0 currently. So the required number of 5's will be 1. That's what's going on inside our code. Okay. Now coming to the next step, how do I get the number of 5? Definitely 5 happens to be the least. So for example, if I would have required two fives instead, then 25 would have been the minimum. So let's suppose with two fives I also require 1 2. Then 25 into 2, 50 would have been the minimum number of the minimum amount, the minimum multiplier through which I'll be able to get at least the required amount of zeros. Okay, so in current case, 5 happens to be the minimum. Now, if I say that 5 is a number and multiplying the current number by 5, I can get one number of 0. Can I say the same thing about 10? Well, definitely, because 5 also divides 10. So, the observation that comes out of this thing is that if I am able to get the number which is smaller than m, which is smaller than or equal to m, but is also divisible by 5. So, we can say the greatest number which is smaller than or equal to 5, smaller than or equal to m, but also divisible by 5, will be the number that I am trying to target as a multiplier. Okay, so if you are not able to understand this, please rewind and watch. This is um, very typical maths stuff, and you'll have to understand this on your own. There is no easier way to understand this maths. I'm not saying that there is no easier way to solve the problem. There might exist one, but this is the maths that I used. And if you want to understand it, just rewind and watch again. So currently I need a number that is smaller than or equal to m but greatest and the multiple of 5. So that's what I need. How can I get this thing? If I take modulus of m with 5. So 5 is our example number. It can be anything. Okay. So I'll get the remainder. I'll get the remainder if I do this thing. And now if I subtract the remainder from m, can I say that the resultant number that I will get will definitely be the number that I'm looking for? It might be 0, it might be 5, it might be 10, it might be anything. But I can guarantee that it is a maximum number in the given possible range. That is a multiple of 5. So this is the key thing that I have used to solve the problem. Let's see at the code again. So this is the part that I just explained. So what does check do? I give, so let's suppose I say that, okay, the given guesses are already there. You make 5 zeros, that g is equal to 5. It will tell me if it is what is the maximum number that I can get through which I can get 5 zeros, or it will just return 0. Okay, because it might be a possibility that, for example, if I need 5 and m was actually equal to 4, in that case the resultant number will nothing but 0, only in that case. Not specifically in that case, but it is a very high possibility that I'll get zeros a lot of times. So that's what it does. And now I looked at the constraints again. It says that n raised to power 9, n and m can go. So that means the maximum number of zeros that I can have is 18 towards the end. So what I do is that I declared z equal to 18 and I started by checking. So in any case, if answer is greater than 0, that means that I can make the required number of zeros and I have my target value. In that case, I'll just multiply answer with the current number and print that value and return. Otherwise, if I cannot make any of the numbers is 0 towards the end, that means no round is possible, then I simply print n into m. M is given the name to the variable in the question and k that I have used here. So this was a problem D. So the next problem E, the humanoid. And again, it took me one extra try to solve this problem, but that was just because I used integer instead of long overlooking to the constraint. So please avoid this problem, this mistake actually. So without wasting further time, let's look at the problem. So there are n astronauts working on some space station. An astronaut with the number 1 to n has a certain power. So an astronaut with at number I has a certain power associated with him, that is AI. An evil humanoid has made his way to the space station. The power of this humanoid is already equal to H, and the humanoid took with him two green serums and one blue serum. That's given to us. Okay, let's see what the humanoid can do, the evil one. So he can do one of these three things at one time. So he can absorb a astronaut with the power strictly less than him, and by doing so, his power increases by the astronaut's power divided by two and the floor of that. Okay. The second action that he can perform is that he can use the green serum. If he has one, of course, he should have the serum to use it. And what will green serum do? It will double his power. Similarly, he can use a blue serum if he has one, and the serum will triple his power. So we have to output the maximum number of astronauts the evil humanoid is able to absorb. Okay, so this question is that I cannot say exactly that it is using dynamic programming, but I use dynamic programming with three states to solve this problem. So in case you do not know dynamic programming, I would first recommend you to go ahead, learn, and do some questions on DP, and then just return over here and try to solve this problem again. So I will not be able to write anything because 3D DP is like just next to impossible to um, write it down using a pen and paper, and yeah. So I will just hop onto the code straight away. So N is the number of astronauts, H happens to be the initial health of the humanoid, and I take in the input as their health. Now I define my DP in three states. The first state is that the number of astronauts it has already absorbed. The second state is that okay, if this is one, that it means that he has used one of the green serums. If it is two, then it means he has used both the green serums. If this state is corresponding to zero, that means he has used none of the green serums. Similarly, for the blue serums, the corresponding states are 0 and 1, that he hasn't used one and he has used one. Now I'll sort the astronaut's power because it only makes sense to try and absorb the astronaut with the least power at a point in time. Only then shall we proceed further. So this is quite intuitive. Then I basically initialize my DP, everything with 0. And I also say that when he has not absorbed any human, he has not used any serums, neither green nor blue, he already has a power of H. And now I will be using push DP. Now what is push DP? Push DP is nothing but trying to use the current state to influence the future state. And we also have a thing called pull DP. What is that? It is the type of DP in which we determine the answer of current state using the previous state. So we are pulling from the previous state. And if we are at the current state and influencing the future ones, it is using push, that we are pushing our data or our knowledge to the future states. Okay, so I write three loops over here, and so I'll just try to use all of the three operations so that I'm able to explore each and every path. So the first operation that he can do is of the condition that if his current power, so dp at this particular state determines the power of humanoid. So current state, if in current state he can absorb an astronaut, then this will determine that okay, he has absorbed plus one astronaut and the power will be definitely greater. So you don't even need this max function over here. You can just simply write that okay, this will be the power. Okay. Now if he has a green serum left, then he'll try to use the green serum over here. That means he'll use one of the green serums and the power will be maximum of current of that current state, and current state multiplied by 2 because it doubles the power. Same goes for the green serum. Same goes for the blue serums. And now, how do I determine the answer? If at any point in time, if at any point in time for any of the astronaut state, that means if the first state has a power that is not equal to 0, that means I was able to absorb that astronaut over there, the ith astronaut. So if I reverse loop, in the astronaut state, and in either of the remaining two states, I am able to find a power that is greater than 0. It means that I have absorbed that astronaut, and that's the maximum limit. So that's what I do. I reverse loop and I try to figure it out. If I have a power that is non-zero, then answer will be I, and if there is answer, we'll break. Okay, and then we simply find the answer. So this is a typical DP problem according to me, and I use this method to solve it. So let's move on. Next up is problem F. Now at this point in time, I had really less time left in my contest, and I decided to invest that time in problem G instead, and I was fortunately able to solve that problem. The problem F, I upsolved this problem. I was not able to solve it during the contest. So let's discuss the problem now. A positive number x of length n is given in a base of p. That means it's not 10 random. Generally, we use standardly as the base 10 of any number. So let's see how the base system works first. So for example, in 10, we write numbers from 1 till 10 minus 1. And then we add, then this thing just cycles. So for example, if we reach 9, then it will be 10. So 1 goes over here, and this place will again start from 0. We'll go to 9, and then this number will be added again by 1, and this number resets to 0, and the cycle goes on. So similarly, in binary ways, it will be 0, 1, and 1, 0, 1, 1, 1, 0, 0, and so on. So you must be familiar with this. Now what happens if the base is 3? It will be 0, 1, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, and so on. So this is what is basically meant by having a different base. So let's go on. So it's written on the blackboard. The number x is given as a sequence to us. Okay. And the digits of x in order from left to right. So basically, it's no change from what we see generally. Now this guy, I do not know how to pronounce this, is very fond of all the digits of this number system. So he wants to see each digit, each one of those digits at least once. Now this is a little confusing statement, but I'll let you know what it means. So for example, if we have a base 10 and we are given the number 1 over here, so by going till 9 and then 10, so at each and every step, he is able to see those numbers. So for example, if you go from 1, 2, 3, 4, then you do not need to make a number that consists of all of those digits. He is already seeing these digits as you progress. Okay, so let's read the problem further. In one operation, he can take any number x written on the board. So there is only one number written on the board. He can take that and increase its value by 1. So for example, if it's 2, 3, 4, then is already seeing 2, 3, and 4. And then he can use the base 5. So let's try to write this thing down as well. So it's 2, 3, 4 to the base 5. He can make this 2, 3, 5. He can make this 2, 4, 0, 2, 4, 1, 2, 4, 2, and so on. So this is how the things proceed. And we want to make sure that he sees all of those digits, and we have to tell what are the least number of such operations required. Okay, now the problem is not that intuitive to think at once. At least it took me a while to figure it out how we can do this one. So let's take the base 10 example, since that's what we like the most, and see how things work. So for example, if I give you a number 15, then I say that I want to see all the numbers from 0 to 9, because that's the only possible thing that we can do. Then what we can do, we go to 16, 17, 18, 19, 20, 21, 22, 23, and 24. So this is the last number where we are able to see all of the numbers. Now how can we say that this thing works? So again, I would like to jump straight into the code and explain simultaneously. So here is the accepted code. Now let's see how to solve this thing. So first of all, the number given to us is in form of a sequence. So I take the number of those numbers and p as the base. Taken the input, declare a set. Now the work of set is to tell me that how many number of basically how many different numbers I have already seen. So that's the use case of this set. I take in the input as the and also simultaneously inserted into the set. Now the problem can be broken into two statements, or basically two cases. One is where I have already seen the numbers greater than smaller than the units place, and another where I haven't seen that. So for example, if I say that I have a base 5 and I give you a number which has 1, 2, 3. So I give you this number. In this case, we can obviously say that we have already seen numbers 1, 2, and 3. So we just need to see 4 and 5. So this thing comes pretty intuitively, like, yeah, we can just simply what we can do, of course, not 5, only 4. We can just say that 4 minus 3 will be our answer. Okay, so the greater number, the number that is greatest uh, in the base, basically p minus 1, p minus 2, and so on, will be the greatest numbers that we haven't seen already. And we just subtract the units place because the number smaller than the units place we have already seen. So this is one case. Another case can be where we haven't seen all of those digits. For example, I give you a number 2 and 4 to the base 5 again. Sorry. So in this case, we are definitely sure that we'll have to make at least one round cycle. By that round cycle, I mean that setting the units place back to 0 and then growing up from there again, adding 1 and so on. So I can be sure of one thing, that any number that is greater than 4 but less than p minus 1. So from number 4 till p minus 1. I will see all those numbers. Let's say that the base is 8 instead. Then I'll see all the numbers 4, 5, 6, 7, and so on till 7 basically, because 7 is equal to p minus 1. So I do not need to worry about these, but I'll definitely have to make these operations. So in that case, the answer is at least p minus 1 minus the number at our units place. This is the least operation, and after that we have to again cycle up back to the first case. And what will be our first case? From 0. From 0, we have to go to the number that is greatest but unseen yet. Okay, from 0, go to a number that is greatest plus unseen. Okay, but here is a catch. Here is a catch. Hold on. Whenever I reset my number to 0, I'm also altering the numbers that are beyond that. So, for example, in the tens base system, if I am at number 199, I also alter the number like this. That means I'm also seeing 2. So this is a random case, but there is a possibility that you may not need to do any further operations in this case. So for example, if I take a number 2, 2, 4, okay, and then you can see that if it is to the base 5, then I can go like 2, 3, 0 and 2, 3, 1. By doing only the two operations, I have already seen um, all of the digits present in this base. So from 0, we go to the greatest and the unseen. Okay, so these are the two basic cases where we can split the problem into these two basic cases. Let's see how our code deals with this. So we had taken the input and I declared equal to 0. So this is so that I can from 0 I start by finding the first number that is unseen. Okay, it might be smaller than the units place. Our units place is at a of n minus 1. And this might also be greater than that. So here is the place where our question splits up. Answer will be definitely the answer. No need to explain what it stores. So if t is not equal to a at n minus 1. Okay, if it is not equal to a at n minus 1, we need to do certain number of operations. Otherwise, we are all set and we will just see that what we can do. So basically XOR just means that these two numbers are not equal. Of course, if these were equal, then XOR would result into a 0. Now if these two numbers are not equal, then we say that okay, answer is equal to p minus n minus 1. That means that we at least need to go till p of minus 1. Um, then we say that okay, I declare a carry. Why do I declare a carry? To deal that 199 case. Um, so in that case, I'll definitely have to uh, recycle through that, go to zero and then run in cycle and grow again. So I'll be making a new number. How can we make a new number? We'll be adding the things from the right of the array to the left of the array, and then see if the number is equal to base. That means that we'll have to reset the next bit as well. Otherwise, we are good enough. So, for example, while carry, so carry should be there, and yet I should be greater than zero. So that's just running the loop from right to left. We do an AI plus plus because the number definitely increases. um, then we can say that if AI is greater than equal to P, that means we have reached the base and we need to reset. In that case, we do not tamper with the carry and we simply say that it's modulus, or you can simply subtract P from it. That's one and the same thing. Otherwise, we'll just make carry equal to 0 and insert the new number. Once carry will be equal to 0, we'll break out of this loop and the new number formation, um, like for example, let's take the base 10 again. So 199 to 200. So we'll insert zeros and 2 in our sets, or even if it's 198 or something like that, it will go to 199 and we'll see that thing. Okay, so that's what this loop does. Now if carry is still there, because we are running the loop, so what happens if we have a number 999? What will happen? We'll go 000 and one carry will still be left, but our array iterations will be over. In that case, we also need to insert one into our set. So we do that, and after doing that, we also insert a 0 because now we are sure that okay, the number that we have is definitely the number will go to 0. So a of n minus 1 will be 0 now, definitely. Yeah, we are sure of that, though I haven't explicitly tempered this number because we need this value in order to do further calculations. But yeah, made this number 0 and assume that we have seen at least one 0 so that we do not waste any of the further operations. Now once done that, and this is done with the formation of new number, now again t is equal to a at n minus 1, and we are finding the greatest number that is unseen. Remember I wrote over here the greatest plus unseen stuff. That is what this particular loop is calculating. So t is equal to n minus 1. Definitely this number is a seen one. T must be greater than 0 because we have already reached 0 at some point in time. And we also make sure that we have seen this number. So till that time we subtract it. Once it's unseen, we simply add this. So for example, um, in the base 10 only, let's take the example 199. So we go to 200 and we are sure that we have seen the 0 now. Now it will loop down from 9 and pause at 8. So from 0, now we need to go at 8. So we'll just simply add this 8 to our answer. And this will be our final answer for this particular case. Otherwise, now this else corresponds to this, that if t is um, equal to n minus 1, this means that we have at least seen the numbers already till n minus 1, a of n minus 1, that is the units place. In this case, we will have to iterate just till p minus 1, just till p minus 1. So for example, if I have a base of 7 and I say I have a number 1, 2, 3 till 7, or maybe 1023, this is a number that is given to us in base 7, then I'll just have to go from 3 to 6, that's p minus 1 minus our units place. Okay, so that's what I add over here. So t is equal to p minus 1, and we again loop back till the number that is greatest and unseen. And so in this case, if so this is the number greatest and unseen as of now is 6. It could have been that we were provided with number like 0, 6, 2, 3 in base 7. In that case, we'll just go from 3 to 5. So 5 in that case will be greatest plus unseen. And we add this into our answer and just print the answer. So let's discuss the final problem G, restore the permutation. A sequence of n numbers is called a permutation. Of course, we already discussed the definition of what a permutation is, but again, So if every number from 1 to n occurs exactly once in any random order, then it's a permutation. For a permutation P of length n, you can make an array B of length n by 2. So n is definitely even over here, and a permutation and a sequence B can be made out of it, which is exactly half of its length. And how is it made? It's made by saying that max of P are 2i minus 1 and 2i. So take two consecutive elements and take the max of that. That will be the position, that will be the value of B at that position. So let's take an example. So 1 4 2, let's take this example 1 4 2 3 5 6. 1 4 2 3 5 6. So take maximum of these two, which is 4, take maximum of these two, which is 3, and max of these two, which is 6. So this is our B. Okay, in simpler words, this is what our B is. So you can see 436 and 436. Again, you can also, so this is just the explanation of that thing. Again, you can see 436 here as well. So the permutation is lexicographically smaller if at any index that is smaller, and so basically lexicographical smaller permutation. What does that mean? So for example, we have a 1 1 1 2 1, and we have a 1 1 1 3 1. So at an index which is either like this. So in this case, this will be the lexicographically smaller, or if it was 1 1 2 1 1 and 1 1 1 3 1. And this will be the lexicographically smaller permutation. So what we can say mathematically is that if there is, so the smallest index where there is a mismatch, the permutation with the lower number at that point is lexicographically smaller. So that's what is meant by lexicographically smaller permutation. Okay, let's see further. So we are given the input as test case is the number of n, and the permutation, and the not permutation, the array B of length n by 2. And we have to output the lexicographically minimal permutation P such that you can make an array B from it, or print -1 and claim that it is impossible to do so. So let's see how we can approach this problem now. Let's take an example of 436. 436. So let's say that these are the blanks that I'll be filling it with the numbers that I do not have. So the numbers that I don't have are 1, 2, 3 I have, 4 I have, and 5 I do not have. So in order to have lexicographically smallest possible permutation, I will try that the minimum possible element comes at the start. So that's one possibility. Or maybe I can say the maximum possible element. The maximum possible elements come towards the end. These are the two possible ways in which I can think of this problem. So this will be our basic try to solve this problem. But also there is another possible catch over here, that we also have to ensure that this number should be less than the number that we are pairing it up with. So for example, this, and this, I must make sure that the number filled in the dashes are definitely less than the number that it is being paired up with. So how can I deal with this problem? So the answer is binary search. And what can be done? So let's suppose I make a set out of it. So I have 1, 2, 5, and let's suppose infinity. And I try to do a binary search with 6. So why do I'll definitely get infinity using this. And by assuming the standard implementation in C++, I'll get infinity. And the number just before this number will be the maximum number, will be the maximum number that I can fit in this blank, this particular blank. The number that I get by doing this will be the maximum possible number. Also, if I am not able to get any number which is less than 6. So for example, I had an array of 7, 8, and infinity, and I try to binary search 6, and I'll get 7 over here. But 7 is not smaller than 6, so the permutation in B, then when we compare 6 and 7, when we compare 7 and 6, the number that will go into B will be 7 instead of 6. So we must also make sure that this number is smaller. So let's hop on into the code and see the implementation. So this is the accepted solution. So I take in the number n and declare m as n by 2. Again, I like to use binary operators more, so I did that. Sorry, bitwise operator. So I declare a set in which I'll be using the binary search again and again, so that uh, the order maintained is always in the sorted order. I take in the input. Sorry, before taking in the input, I add each and every number inside the set. Okay, from 1 to n, I add all of the numbers. Then I declare an array B of size m to be precise, but it's half of n again. And then I loop and I take in the input. Okay, then I run a loop till m, that is rn by 2, and I search for that particular number inside the set if it is not present in the set. Okay, so if it is not present in the set, that means that we have redundancy. That means that B was given something like this, and we definitely cannot have two numbers together. Two equal numbers, we cannot have those, or maybe a number out of. So, for example, if I say I have 1, 2, and 100, so this is not a possibility, definitely. So, in this case, I will not be able to find a number, or either I'll not be able to find the number, or I have already removed it. So, the answer will be -1, and I simply return. Otherwise, I'll remove this number. So let's also have an example simultaneously to help us. Let's take 8745 as the example. Okay. So let's take 8, 7, 4, and 5 as the example. And these are the dashes that we fill. Okay. And let's also make the boxes to understand the pairing. Okay. So first of all, insert, I insert all the numbers 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and then I see that I have 8, I find it and I remove it. I see I have 7, I find it and I remove it. I see I have 4, I find it, I remove it, and same for 5. So that is what is being done till this part. Now I insert an infinity in the answer so that I do not go out of bounds. Otherwise, you can obviously check for set equal to end, set dot end for the iterator. That's as per your choice. I like this implementation more. Now I create an array A. So A is corresponding to these blanks. These blanks are all bound in the array. Okay. And now what I do is that I iterate from right, which means that I'll always try to get the maximum number towards the maximum end that is possible. What I do is that I try to find the lower bound of bi. So this will return just greater than just the greater number than 5 in this case, which is 6. Now what do? I perform certain checks. So if itr is equal to st dot begin, that means that I'm already at the begin part. Now I am sure that this number is just greater than the number I searched for. So there is no lesser element present, and the answer will be -1. Otherwise, I take iterator to previous of its iterator, and I simply erase this iterator and give my array the value. So in this case, I see that 6 is just larger than 5. So I take previous of this, which is 3. I insert 3 over here, and then I remove 3. That's what I do repeatedly. So now I will come to 4. At 4, I'll do the binary search again, and I'll be able to find infinity this time. The sorry, I'll able to find 6 this time again, and the number that I find just smaller than 6 will be 2. So 2 will be placed over here. Now 2 will be removed as well. Now for 7, I'll do a binary search again, and this time I'll get infinity. Let's change the color. This time I'll get infinity, and the number just smaller than infinity that I have over here is 6. So we'll be able to fill 6 over here. Again, binary search for 8, and this time the number just smaller than infinity is 1. I'll get 1. 6 was removed previously, 1 was removed this time, and we successfully performed the filling of array A. Now you can just simply print one number from A and one number from B as the answer. If either of the condition was violated during the process, the answer will correspond to -1. That's what I've done. So this loop I explained, and now I just print AI and VI and just the end alert last. So that's it for all the problems. Hope you enjoyed the tutorial. If you enjoyed, then Do give it a like and subscribe to the channel. Also, feel free to ask any of your queries or doubts in the comment section below, or you can also discuss new approaches over there. Thank you.